For your patience, we had some AV difficulties. Unfortunately, due to timing, we didn't have a time to do a sound check and AV check early. So anyway, but thank you.
No, well, thank you everyone for joining us. My name is Domingo from the University of Waterloo in Canada. I'm interested in, I enjoy studying programming languages and operating systems. And I didn't come from audio background, but I did an internship on the Android audio team, and I mainly worked with Glenn on our Dataflow project. Could see that as an alternative to thread programming, which is the dominant way of writing the framework in the Android team.
Hi, I'm Glenn. I'm from the Android audio team. And for most of my time at Android Audio, I worked on latency and performance. But most recently, I've been looking at ways of restructuring the Android audio framework internally to make it easier to maintain, easier to add features and things like that. I haven't been working on the application level, but just the internals. So today we're going to show some work that Domingo and I and some others at Android have been doing over the last couple of years to try to look at new ways of structuring our operating system internally. And this is kind of early work in progress for us, and we want to share our experience, both positive and negative, with what we've done so far. I was expecting that this ADC was going to be devoted to Sol, but it turns out that's not quite true yet. However, fortunately, the Sol beta was just released a couple of days ago, but it's still an exciting project, and I really encourage you to check out Sol. Sol was first announced a year ago at ADC, and it's an exciting new programming language, specifically a domain-specific programming language that's intended for audio applications. Real-time audio. We had a great talk this morning about real-time and what it means, so I'm not going to go into detail about real-time, but basically the concept is you have an audio or MIDI or similar signal coming in, you need to process it and produce your results in a guaranteed response time, typically on the order of a millisecond or low milliseconds. Sol uses something called the graph programming model, directed graph programming model, where you have nodes and edges. Sol calls the nodes processors, and it calls the edges connections, but it's just a similar concept. And you notice it's directed. All the arrows have a head and a tail on them. Here's one example from the Sol Playground. If you haven't already checked out the Playground, I strongly encourage you to try it out. It's a lot of fun, very easy to use, great examples, and you can load up one and then try making modifications and learn from that. Again, here's a graph. We have nodes and edges or processors and connections. This is a simpler example. It's called the diode clipper. The bottom code on the left shows your processors or nodes, and these are essentially equivalent to a C++ class, except they have one very special method called run, and that's where your DSP processing happens inside them. And then the graph part comes in the top left part, where we establish these connections between the nodes. And you write the connections in text, but then it's visualized in the Sol Playground IDE. So looking at this diode clipper example, here we have 3 inputs to the diode clipper processor and 1 output. One of the inputs is a stream, similar, basically an audio stream of floats, and similarly for outputs. But the other 2 are what Sol calls events. These are single values, but that have a timestamp associated with them. And every time you get a new value, you'll also get a callback automatically, and that allows you to update your local state based on that. I already mentioned the run function too, which is the other special function. So it turns out that this is a rather standard approach to programming. It's called Dataflow, and it originated in the late 1970s, originally as a hardware architecture, and it fell out of favor because other processor architectures turned out to be much more efficient and offer much better performance. However, although it essentially failed as a hardware architecture, it has had great success in the last 10 years or so as a software architecture. And we see examples of that in things like TensorFlow, Google Cloud Dataflow. Microsoft has something called TPL, things like that. And again, computation happens inside of nodes, and then data passes between the nodes.
Yeah, so since...
I'll keep it now.
Okay. Since you just mentioned programming paradigm, it's simply just a style rank program. And so it describes a class or a family of programs already in the same way. And for example, these Sol programs, they're written in Sol language, but could be also written in real-time Dataflow. So just different under the same paradigm. And so I'd like to jump in and talk about some common programming paradigms before explaining our rationally choosing Dataflow. So usually we compare declarative and imperative. And the interesting candidate here is supervised machine learning. I think Glenn has some great comments on it later on. And so in the declarative land, we write programs by specifying a set of constraints and maybe a set of desired results. And we tell the computer what we want to achieve, but don't specify how. So the compiler and interpreter has a lot of freedom of choice what to do. And so Dataflow, in Dataflow, the nodes are representing computation modules. And data flows between floating edges, but like we don't specify the evaluation order or the concurrency, parallelism, etc. And also functional programming also falls in the declarative lands. You can imagine expressions or the instructions are written in mathematical types and statements. And computation happens when we substitute or reduce statements by equivalent expressions. So this has this really nice consequence of something called referential transparency, which just means that the output of the program only depends on the input. And on the other hand, in imperative programming, we tell the computer exactly what to do, has very little leeway. And I guess a good sign you can find in imperative programs that there's always a current step, where you can see the arrow on the screen pointing what exactly needs to be done at this time.
So Domingo mentioned the current step pointer, the arrow. This is critical to imperative, and this is one way to recognize imperative programming is if you have the concept of I'm here, I'm at this place right now. In assembly language programming, the current step is called the program counter, or PC. It's also called instruction pointer, or IP. And here's an example of an ARM assembly language program. The PC is pointing to the first instruction, and then as it executes each instruction, it steps through. So I was really interested in where did the PC come from? Because, I mean, every computer I've ever worked with in my whole career has had a PC, and I wondered, like, why? Well, it seems obvious now, but I was really curious. So I did some research. I discovered that John von Neumann, who created the first stored program computer in 1945, had something to do with it, but I didn't know exactly how. So I found his early paper on the EDVAC computer from 1945, and I skimmed through it. It's quite difficult reading, but it's really interesting also. And I found a page that seems to describe the PC. So I think that John von Neumann invented it, but if you can find an earlier reference, please let me know. And one of the things that has happened ever since the invention of the PC is that it's permeated everything that we do. We have control flow structures, we have while loops, for loops, break statements, continues, switch statements, we have exception handling, blah, blah, blah. It just goes on and on and on. And I believe it's taken over our lives, this concept of control flow. And I think it's time to consider something else. It's a lot of complexity. The PC is actually just one register inside of a computer. There's also the full general purpose register set, which often has like 16, 32 other registers with it. But I believe PC is the most important register. That's a hardware register set. When you virtualize it or make essentially a software instantiation of it, it becomes a thread. A thread is the unit of execution. However, the thread is not a complete virtualization of everything that you need to do computation. It's only the processor register set. The memory is still there, and that's still physical memory. That is not virtualized. You may have heard of virtual memory, but that's a different concept. So if you have multiple threads in your program, they each have their own virtualization of the register set, but they're sharing the same memory. And this results in terrible things, which you learned about this morning at the real-time class. The worst of all is race conditions. Here we have two threads that are both trying to access the same memory location, and of course you need atomics, you need locks, or things like that. There are many other problems, in my opinion, with threads. I believe that they are very difficult to scale, in particular, like to parallelize, to take advantage of multiple CPUs is quite hard with the thread programming model. And fortunately, there are options. There's alternatives. There's other programming paradigms beyond imperative programming and beyond threads. And I'll turn it over now to Domingo. Oh, actually, I'm keeping this.
Yeah, so as Glenn mentioned, there are good alternatives to imperative. But first, I'd like to go for like two special cases of the Dataflow paradigm. So they are like so pipeline and spreadsheet are like simplified versions of Dataflow, and we'll see why. So in the pipeline case, for example, in shell programming, you have a series of commands, and you have exactly one input and one output. So you can sort of see that as a sort of linear or degenerate directed graph. And in the spreadsheet example, you can visualize each cell as having one output, and each cell depends on multiple other cells, and the output of the cell could be used in multiple other places, but at any given point of time, we know there's only one unique value that it outputs. So we can also model this as a directed graph, and I think you have. Yeah.
So this is a complicated complicated table. Don't bother trying to memorize it right now. But the key points are, as Domingo said, first of all, that a pipeline is linear. It's not a full directed graph, and also that both pipeline and spreadsheet, each node or each cell only produces one value. That value might be consumed by multiple other nodes, but it's only producing one. So they're essentially specializations or cases of general data flow. And general data flow uses a directed graph, and nodes can connect to each other essentially arbitrarily, and nodes can receive multiple inputs, can receive multiple outputs. As in Sol, the data can be either streams of data or it can be single values. We make an additional distinction between regular data flow and real-time data flow. And I would say that Sol is a case of real-time data flow. And it's not just that it's applied to real-time situations, but it's the way that it's designed internally and some of the trade-offs that are made inside. Certainly, as we saw in the real-time talk this morning, there's a lot of clever programming tricks that you can use to make your program real-time, and that is essential if you want to make it real-time. You have to do everything that you heard this morning, at least in the thread programming model. But there's another thing that I believe is also essential, especially in data flow, and that's to limit your data types. Don't use arbitrary data types. Instead, focus on what I call plain old data or pod data. This is things like primitives like floats and ints and bools. Also, combinations of them. You can have arrays, structs, things like that. Those are much easier to handle in a real-time way and to handle with data flow. Once you introduce arbitrary pointers, arbitrary objects, you introduce things like memory allocation, references, destructors, constructors, all that kind of stuff, and it can be very hard to implement that in a real-time way. This morning, oh no, password. Okay, Domingo is going to keep talking. You're going to ad-lib while I type in a password.
Yeah, so in the Dataflow library, there are different parts of the API. I think there are 4 parts. The first part is the design phase, or where you build a graph, you specify all of the nodes and the connections. So that's like before your value graph, and you can do all sorts of evil things. So you can allocate memory, you can use logs and whatnot. And after that, you can, oh, right, that's yours. Okay, I'm not going to do that.
Okay, so we've seen Dataflow, we've seen various forms of declarative programming. I just want to throw this out there just because it's related to this concept of programming paradigms, which is machine learning a programming paradigm? And this is a very controversial topic. I've talked to a few people. People feel different ways. I want to give you my take on it, which is, yes, it is a programming paradigm. Let's say we have a computation which is the product of a sum and a difference here. And I'm showing it two ways, traditional style at the bottom or as Dataflow at the top. Question is, can you do this with machine learning? And what do you think? Yes, okay, good. That's the right answer. So what we do is we first get some training data. ML requires tremendous amounts of training data. Here we have that table on the left. The ABC are the inputs, and then we have the corresponding results. If you want to check, these are all doing the product of a sum and difference. But that's all we have. We don't have the we don't have the general purpose formula. Then we feed that into an untrained model, which is essentially random. We iterate it over it many, many times, do backpropagation. Eventually, we have a model that works pretty well for the training data. Then we test it with new data that we've never seen before. It's called the test data, and we see how well it does. If it does okay, great, we're done. If not, we need to go back, tweak the model, maybe get some new training data, whatever. But one thing that's very important is you do not, I'm going to click the button just so that we don't get that problem we just had with the password. If it's not good enough, one thing you don't want to do is take your test data and add it back into the mix of your training data, because it will result in this thing called overtraining, which is a very, very bad thing. Anyway, once it's good enough, you now have a deployed model. You can use it with live data, and you get predictions. The one interesting thing is the predictions are approximate. So you may not get the exact results, but you'll probably get something that's pretty close. And every once in a while, you'll get something that's just completely wrong. And this is just something that comes along with ML. So Sol is Dataflow. In particular, it's real-time Dataflow. Domingo and I and other people in Android Audio have been implementing this thing called libdataflow. It is serving different needs. Sol was targeting application programming, especially for audio. We're targeting use inside of the operating system. We want to restructure parts of the operating system to make it a little bit easier to maintain. The other difference is that Sol chose to create a domain-specific language. We're instead using ordinary C++ and just doing an API that implements the Dataflow model. I want to show you a little bit about what that looks like. Our library, we want it to be real time, and yet there are parts of what you need to do with graph building that require memory allocation, that might require I/O or other services that are not possible in a real-time environment. So what we did was we took the library, we partitioned it into different APIs. Some APIs that are usable at design time, and other APIs that are usable at runtime. So the ones on the left can use more dependencies, let's say from the standard library. They can do memory allocation, they can use std vector, std set, things like that. Whereas the runtime API has minimal dependencies. I haven't looked at it recently, but it's just a few undefined symbols when you look at it, and they're very basic operations like memcopy.
Yeah, so we talk about my own experience working with libdataflow, and I'll talk about the good things first, and then we can look at some of the trade-offs they had to make. I guess the most important thing that I got out of this is that the nodes they could be nested in other different nodes. And so this has a good benefit of being testable and reusable. And once you test it, you know it's correct, you get a guarantee of the performance as well. And this, as you imagine, leads to less duplicated code. So it's more efficient as well. Another thing that I notice is that you can get an arbitrary untrusted node and put it in a graph. And the graph essentially run in a sandbox environment. So we achieved that by, well, the lib data flow achieved that by supplying limited number of system calls as well as copying plain old data mentioned by Glenn. And that gives us like the security guarantee, which is pretty nice.
So again, we're taking a node that we don't trust, we're putting it in a sandbox, and you might ask, well, why can't you do that with other code? Why do you need Dataflow to do this? Well, yes, you can do this with imperative programming. The difference is with Dataflow, it's extremely easy because the only interfaces are the data coming in and the data out. And that's plain data, so it's much easier to take a node, isolate it, and it doesn't even realize that it's being isolated. Another example of moving and partitioning your nodes is you can take a Dataflow graph and you can draw a line, or a dotted line through part of it and say, okay, I'm going to run part of this on my main application processor. I'll run part on a digital signal processor. And again, because it's simply data with no pointers and things like that, it's much easier to partition. One application that we've seen for this as a potential is logging, in addition to audio, because logging has a lot of the same characteristics as audio. Our logs are often created by real-time threads. Those real-time threads can't afford to take mutexes or allocate memory, so we take the logs, put them into a FIFO, and then the rest of the log processing can happen on ordinary threads, again, using the Dataflow model. Dataflow is also really nice because it allows you to take the same output and tee it to multiple inputs, as we've seen here with this filter going to error and statistics. This next possible use case is one that I haven't actually tried out, but I believe it has potential. Doing machine learning requires tremendous amounts of training data, and it requires the ability to do something with a decision. You make an inference, but then you have to be able to have the system do something with it. Here's an example. Let's suppose you wanted to automatically control the volume of device or phone or something like that based on machine learning. My hunch is that we could take the volume taps, the up and down volume taps, and use that as training data, and based on that, develop an ML model. And then, once we have it trained, we could take a manual step where it's applying a gain and replace it or augment it by prediction. And it could even be a combination of both the hardwired gain with the predicted gain. Again, this is not something that I've actually done, but it seems like it might work. And the cool thing is that it's something that ML people could work on without the rest of the team having to get involved. They just give them the graph, and then you just look at the graph at a high level. Now, Dataflow is not perfect by any means. It definitely has some problems. First of all, there's certain types of programming that it just doesn't fit at all, so you can forget about it. But even when it does fit, it's a new way of programming. It's a new way of thinking, and requires studying and looking at examples. It's definitely a new way of debugging because you don't single step through the code in the usual way. And one thing that we found recently during Domingo's project is that we had a large amount of legacy code that really theoretically should have fit into the Dataflow model very easily, but it wasn't structured that way. And so it turned out to be harder than we thought it would be. So instead, we're taking a new approach, which is to more gradually introduce Dataflow in certain selected places and learn from that experience rather than trying to redo the whole system with Dataflow. So I have a few assignments for you, the audience. First of all, I really want you to try out the Soul Playground. It's a tremendous amount of fun, and I think you'll enjoy it, and with great examples. In the next slide, I have a link to some videos where you can learn more about Dataflow and real-time Dataflow. Some of the videos are just like 6 minutes, 10 minutes long, so I think they'll be easy to watch. If there's one takeaway, though, that's even more important than that, I would say question threads. All right. I think that we have gotten used to, we've accepted threads as being the way to program, and I don't believe that we can continue to scale based solely on the thread programming model. So consider other programming paradigms. Certainly imperative is one valid way, but also there's functional, there's machine learning, there's Dataflow. Anyway, be open. Think about other ways of doing things. Even if you don't use them, I believe it can positively impact your code that you do write. And then finally, of course, ask questions, which is what we're here for. Normally, we would be on really, really strict time, but fortunately, because it's coffee break, we actually can, I believe, take a couple of questions. But if you need to get coffee, certainly go. I'm going to leave the link up here. This has links to the videos and also a discussion group where you can post questions about Dataflow. Any questions?
So my question, they're all wrapped into one question, which is, if it's, like you're talking about sandboxing and predictable performance, and especially in the audio space, how are you dealing with large pieces of data? And like, does the compiler handle passing huge amounts of data between all those nodes, and how is it actually sandboxed and actually predictable performance? Okay,
great question. It is two questions at least in there. First, let's talk about large data. I said that Dataflow works better with pod data types, basically data without pointers. So you might wonder, well, how can I efficiently pass a very large block of data from one node to another? Okay. Well, I skipped over one little detail, which is it's OK to hand off data. So if you have, for example, a reference to data and you want to pass it off to the next node, that's OK. And it doesn't require a mem copy. What you don't want to do is to share the same data, especially if it's mutable. And also, if it's read-only, it's also OK to hand off. So we can efficiently move data through the pipeline as long as it's being handed off. Okay. The next one about doesn't sandboxing impact performance? Absolutely it would. So there's no question that if you take part of the graph and put it in a different process with different permissions, it will affect performance. However, that's a trade-off. Sometimes security is more important.
How can you predict performance if you're handing, if your filter could, how could you predict performance if you can be like receiving any size of data?
I'm sorry, I didn't quite understand that. Can you repeat it, please?
So at one point you said, oh, this is super handled because you can predict performance. So if you're doing unit testing on a node, predict performance for any particular node.
I may have missed the exact context, but I think one reason why Dataflow can offer more predictable performance is because a computation depends only on its inputs. And it essentially has what he was describing as referential transparency. And so given the input data, you know that it's going to take a certain amount of time to execute. Your code will not be executing system calls. It will not be taking mutexes. It won't be doing memory allocations. So it will, for that input data, will generally take the same amount of time. Anyone else? Yeah, I see one here. Okay.
Hi. Isn't Dataflow programming really functional programming under the hood? Because we could see each node as a function, and then like the arrow going from one node to the other as function composition. And you just said that each node is only dependent from its own argument. So what's really, also like if you think of languages like Faust, they can also, it's a functional language, but it can also produce a kind of graph that looks like that, more or less.
That's a really good point. I'm going to attempt my view on your question, but I'm also going to ask Domingo to chime in with his own thoughts, because he actually knows more about functional. From my experience, both functional and Dataflow have the concept of pure computation. That is, within a node or a function, it only does computation math, essentially. It doesn't do anything else. It doesn't access the outside world. So those are similar. Where I see difference is that Dataflow is based on looking at data as it moves through a system. And as it's modified or filtered or augmented, basically it's about the movement of data. Whereas I see functional programming more as about the composition of functions. And you can also have functions, for example, that take functions as parameters. You can have functions that return functions. There are operators on functions that combine two functions and make another function. And you can write functional programs where you never see data at all until at the point where you're actually going to use it. And there's also the concept of reduction, but that's an implementation issue. Domingo, can you maybe say what you see as the relationship?
I think you've covered pretty much what I want to say. Of course, I do agree with you that there's all similarities between functional and Dataflow, and of course they're equivalent. I guess the way I see it is that in Dataflow, you see explicitly where each computation module is, represented as a node. And you can do all sorts of things, like you can parallelize certain computation nodes beforehand. And there's this concept of pull and push model in Dataflow. I think this exists in functional programming as well, but it's not emphasized as much as I see it. And in the push model, you sort of compute results eagerly. You compute result whenever all of the dependencies of a node is ready. And the pull model is sort of like a lazy evaluation order. You only request result from your the dependencies of a computation node. So I guess that will be a difference between how the mental model works between the two paradigms.
Thank you. We're at a half hour now after when we started, along with the interruptions. Thank you for attending and for your patience as we worked with the AV. And let's all enjoy coffee, and you can certainly ask us questions.
Thank you very much.